Okay, the Gargemelle experiment, actually, the discovery of neutral currents. Okay, so Gargemelle experiment was actually designed primarily, primarily to discover the W boson, but the discovery of neutral current, which was very important for Gargemelle experiment. The discovery of neutral current was on the 8 on its priority list. It was not a priority, but anyway, the discovery of neutral current was a huge, considered to be a huge accomplishment of Gargemelle experiment. Okay, so first of all, a bit of history. First of all, they tried to check the existence of neutral current at CERN in proton synchrotron, and this proton synchrotron is still working as a proton injector. And at CERN they checked this process, which is a neutral current process, and when they published their result, so the ratio of the neutral current was the ratio of neutral current and the charge current was around 0.03, and it should have been 0.12 according to the theoretical results. It should have been 0.12, but at CERN, when they checked this, when they did the analysis, and they found that the ratio of neutral current and the charge current is around 0.03, which was later, later in 1970s, when a PhD student reanalyzed the data of the proton synchrotron experiment, and he found an error, and then he redid the analysis, and actually the value of the ratio of neutral current or charge current was 0.12 plus minus 0.06. So this was the first hint of the existence of neutral currents. Okay, so now coming back to the original Gargemelle experiment. So Gargemelle experiment is actually a huge bubble chamber, which is around it is in a cylindrical shape, which is 4.8 meter long and 1.8 meter wide, the diameter, and the total volume of this bubble chamber was 12 meter cube, and it was filled with freon gas. Freon gas is the gas which is used in which was used in refrigerators, and now it is banned due to the environmental issues. It is not good for environment. So the Gargemelle experiment, they used freon gas because it is very high density gas. And why they needed that high density freon gas? Because they wanted to because there was no electronic system to accumulate the signal. So actually in that chamber there were several windows. From there, physically the cameraman took the photos of the traces of the trajectories of the particles that were observed in that experiment. Let me show you one of that picture. Okay, here is a picture of let's say a charged current event. Okay, so moving on. Okay, so at Gargemelle experiment, they were looking for this neutral current event plus electron, muon neutrino plus electron, and in return they is muon plus electron. So in general it could also be like anti-muon neutrino plus electron and anti-muon neutrino plus electron. So these both of these are actually the neutral current events. So they were looking for these events, and for every 1500 events it was expected to get at least 5 to 30 these events. I mean, for every 1500 events the expected cross section of getting this neutral current event was 5 to 30, but what they really observed was just 3 events. So they only observed the 3 events, and this was their expected events. Okay, so actually these statistics were too low. So in order to get more statistics, they started looking for another process, which was it could be a muon neutrino or muon antineutrino interacting with a nucleon, and a neutrino, a muon neutrino or a muon antineutrino is produced with a hadronic shower. So they started looking for this process. This is also a neutral current process, and the corresponding charge current process is muon neutrino or anti-muon neutrino plus nucleon, and muon or anti-muon plus hadronic shower. So they actually started looking for these two processes in order to get the discovery of in order to get better statistics of the neutral current events. Okay, now the disadvantage of this choice is that there is more complicated background which cannot be controlled. For example, this process is triggered by a neutrino, and via charge current process it produces neutrons, and then these neutrons later behave very similarly to the neutrino, and so this was the background, and this background was difficult to control, and also there were some fake events which were not so easy to control. Let me show you the picture of that event. Now if you look at the first event, which is actually called an associated star event. So this is called associated star event, which is actually a signal event. But if we look at this event, this event is actually a background event. Why is the background event? Because the fact that we are looking we cannot see the neutrino, because neutrinos does not interact. Actually we are looking for the neutrons, the hadrons. So now if we look at this process is purely a charged current process, because we observe a neutron and we observe a muon. So it is purely a charged current event. So we are observing a muon and a neutron. So this is a charge current event. But if we look at this event, the background event, this is actually, it looks like a neutral current event because we are only observing the neutron here, but actually a muon is produced, but that is not actually detected inside the bubble chamber. So this is a fake, we can say that this is a fake neutral current event. And this was a problem. So how they dealt, how they actually dealt with this issue, let me show you. Okay, so actually what they did, they took the ratio of these background events and the associated star events, which are approximated as lambda s divided by L minus lambda f, where actually L is the length of detector, that was 8 meter, I showed you earlier, and lambda s and lambda s is the mean free path or the interaction length of the particle and of the medium. So this is the interaction length of the screen. Okay, let me take this a little back of the screen, and this is the interaction length of freon gas, which was used as a medium inside the bubble chamber, the dense gas. So all these variables, I mean the lambda c, lambda s, lambda f and L, they are all known, and they expected the ratio of background events or associate star events to be approximately 0.7. So this if these events, if the ratio is 0.7, then it's good. But what they really observed, this was the expectation, but they observed this ratio to be 6. So this was the observation. Now if there are no neutral currents, so if there are I mean if the neutral current does not exist, then B over AS should be equal to the neutral current over AS. The associated star events, those are the charge current events. So if neutral current does not exist, if neutral current doesn't exist, so this should be equal. But what they observed, that the neutral current or the associated star events were actually, okay, I need to correct this here, the neutral current or associated star events were 6, and what they observed for the background events, the ratio of background events to the associated star events was 0.7. So this was the, I mean we can clearly see that the difference between 0.7 and 6. So it was the evidence of the existence of the neutral current events. So neutral currents does exist. So I'm gonna show you the results of the neutral currents and the charged current events. So they observed for the muon neutrino beam, they observed 102 neutral current events and 428 charged current events. And for the anti-muon beam, they observed 64 neutral current events and 148 charge current events, and the ratio of the neutral current and the charge current for the muon muon neutrino beam was 0.21, and the ratio of the neutral current and the charge current for the anti-muon neutrino beam was 0.45. Okay, so now I remind you